All right, continuing on, sequential logic circuits and flip-flops. Okay, so as stated earlier, sequential logic circuits are so called because the functions take place in a sequence. We usually use, not usually, we use a clock signal, which is usually a square or rectangular AC signal to keep everything synchronized. Okay, we keep everything synchronized. And we introduce the concept of a flip-flop. The reason it's called a flip-flop is because the output of it can flip-flop between zeros and ones depending on the input conditions. Okay. And flip-flops are the essential building block of all sequential circuits. Okay. It has two operating modes. Typically, we refer to set mode as 1 and reset as 0. And this is the reset button that you would often refer to in any microcontroller or any system. We say, okay, let's reset. When reset, it wipes everything out. Basically, it goes to 0. Okay. Then the output of these sequential circuits is noted by uppercase Q. At the same time, we have a secondary output. Secondary output, which is simply Q naught. Q naught. The number of values that the output can take, or the number of values that the system output can take, is known as N, or the state. Okay, it's the state, the operating point, operating position of that circuit. Okay, so it's the state of that system. So the output, also known as state, referred to with a lowercase n. It's a lowercase n. N refers to the number of states. Okay, lowercase n. And n minus 1 means previous, and n plus 1 means the next. Okay. So if it's Qn minus 1 or Qn plus 1, it's the previous output or the next output. Okay. All right. So the most simplistic version of a flip-flop can be designed with two NOT gates, the outputs of which are fed as input to the other NOT gate. So let's say you have an input here and you have an input here. Okay. Input to these NOT gates can take on two values, right? If it's 1 here, the output is 0. If the output is 0, if Q is 0, then the input to the other NOT gate is 0. Q naught is 1, which makes sense. Q and Q naught should be opposite. So if Q is 0, Q naught is 1. And that 1 is then fed back to the input. Okay. So that is the first state for this flip-flop. Q is 0, Q naught is 1. This is one state. Each flip-flop can store 1 bit of memory, meaning the output stays, as long as the input is present, of course, the output stays at that state, and we call it as having 1 bit memory. It can store 1 bit of data. Okay, so you require one flip-flop to store 1 bit of data. If this is 0, then this is 0. Sorry. the other way around. The output is 1 here, this goes to 1, and this goes to 0. Okay, so it can flip-flop between 1 and 0. 1 and 0. Okay, so that's the most, that's the simplest example of a flip-flop. But let's take a look at the first one. Set reset flip-flop, hence the name SR. SR flip-flop. SR flip-flop. Flip-flops are noted by a square box with inputs on the left and outputs on the right. So these are the inputs, these are the outputs. R and S are the inputs. And Q and Q naught are the outputs. Okay. The truth table is so called, of course. We've seen that for logic gates. It's the same meaning here. It basically describes the operation of the flip-flop. For any given set of inputs, what is going to be the output of that circuit? Okay, so here we have two inputs, reset and set, R and S. And then you have Q, N, that's the output. So when R and S are 0, the output doesn't change. Output remains in the previous state. If the previous state was 0, it will remain at 0. If the previous state was 1, then the output remains at 1. Okay, so Qn minus 1 simply indicates the previous output. It could be 0 or it could be 1. In order for the output to change, you can apply 0 and 1 to R and S. So reset is 0, set goes to high, then the output Q goes high, which of course where the name comes from. You set input 1, output goes to 1. Your reset goes to 1, output is reset to 0. Yes. It could be used, this is a building block. So it is used to store 1 bit of memory. So the use case for this would be as part of a larger combinational circuit. A simple example for this, it's, as you can see, let me finish with this and I'll show the drawback of why this cannot be used. So if set goes high, output is 1, reset goes high, output is 0. Remember, set is 1 and reset is 0, the outputs. Yes. Memory in the sense it remembers the combinational circuits we looked at, the output does not depend. I mean, the output depends on the input being present. Flip-flops, sequential circuits, the output depends either on the present input or a previous input previous. So it remembers what the previous input was and stores the output or keeps the output as it is. It's used everywhere. These are the building blocks for all circuits that we use. All digital circuits that we use for today, like processors, microcontrollers, they're all based on digital logic circuits. Everything. Yep. So all the memory that we use for RAM, ROM, all of these are basically gates and flip-flops. So RAM is, let's go on a bit of a tangent. So when memory circuits were first invented, it fell into 2 categories: permanent and volatile, or non-volatile and volatile. Volatile meant as long as there was power applied, you could get the output, it could work. As soon as the power went off, everything went to 0. That was volatile memory. Non-volatile is what we came to call as ROM. And so we programmed it. Once it was programmed, it did not depend on an output. Basically called burning, meaning you actually burned the bridges and made the connections, and the connections were permanent. And hence the name read-only memory, ROM, ROM. And then RAM actually is the opposite of ROM, but the name, the word actually doesn't relate to either volatile or non-volatile. It's called random access memory. And that random access memory, RAM, just comes from the fact that when you try to access, you can access it anyway. You don't have to access in a sequence. You can randomly access it, and hence the random access memory name. But if you're talking about volatile versus non-volatile, RAM and ROM are opposite. The naming convention itself doesn't make sense. Okay, the ROMs were, again, they were pre-programmed from the manufacturer, or you could program that, and so came the name PROM, programmable read-only memory. And once you programmed it, that was it. You couldn't like erase and redo it again. Then came EEPROM chips, which were electronically programmable read-only memory. Oh, sorry, not erasable programmable read-only memory. It had a small window, glass window in the microchip itself. You could shine UV light through the glass window and wipe it out and reset it to 0. And then you could program it again. And then came electrically erasable programmable read-only memory called EEPROMs. And now, of course, we have flash memories. The word comes from flashing and reprogramming the chips, or reprogramming the flip-flops and the bits inside. And most of them use NAND gates, and hence most of the flash memory that we use today, sometimes it's known as NAND flash. It's because it uses NAND gates as the chip inside the SSD and the RAM. Anyway, coming back to our class. So it's a fundamental building block of everything we use today. That's the answer. So if R is 0 and S is 0, nothing happens. Output is fine. If either one of the inputs is high and the other is 0, then the output is either set or reset. Again, this R and S doesn't mean the output is going to be R and S. Okay, for the output to be reset, the reset pin has to go high. This is a point of confusion I found in the past. Okay, anytime you want the output, anytime you want to set the output to a particular value, in this case, the output of this flip-flop has two states: set and reset. Set means 1, reset means 0. Okay, but when we go to the input side, the input side R and S means whatever we want to be the output, that pin input must go high, must go 1. So if you want the output to be reset, meaning the output to be 0, the reset pin, reset input should be 1. And if you want the output to be set, then S must be 1. Let's take a 10-second pause while you think over that. Let me know if you have any questions. Does anyone else smell any burning? Machine shop. Right opposite. Anyway, does that make sense? Okay, the input side and the output side. There's always a point of confusion. Like its reset is supposed to be 0. Why is the input R as 1? Okay, there's a difference. And we can verify that with the circuit diagram that we see up here. Right? We have two NOR gates. A NOR gate is basically the opposite of an OR. You take the input and you invert it, right? So if you have a 0 at R and 0 at S, what do we get? It doesn't change anything, because no matter what the input is from Q and Q naught, it will remain the same. See, if the output for Q was 1, let's say, previous state, right? So Q naught would be 0, as an example, right? Then this 1 goes here. What does the NOR gate do? 1 plus 0 gives you 1. Naught is 0. Q naught stays the same. Q also remains the same. Doesn't change. Let's follow it again. If R is 0 and S is 0, and the previous state for Q, previous output for Q was 1, then the lower gate has 0 and 1 as its input. Output remains at 0, Q naught. And the upper gate, you're applying 0 and 0, output remains at 1. Doesn't change. If the previous state was 0 for Q, previous state was 0, then Q bar would be 1, or Q naught would be 1. And those are fed back into the input. So it's 0 here, and it's 1 here. Still remains the same. Doesn't change. Follow. Take your time. Think over that. And that's basically the first state. So as long as R and S are both 0, the output remains the previous state. The output doesn't change. That's the point. If the output was 0 at first, it will remain at 0. If the output was 1, it will remain at 1. That's what is meant by Qn minus 1. Does everyone see that? Okay. Now, when set goes to 1, meaning if set goes to 1 here, then doesn't matter what, excuse me, if set goes to 1 and R is 0, then this input right here, same diagram is going to complicate. So I'm going to wipe this out. Okay, so R was 0, and now S is 1. You're setting, right? Setting. Then this goes high. Q goes high, is fed back here. Output goes to 0. That's fed back here, and the output stays at 1. Okay. Again, it's a NOR gate. So for all inputs, the output to be high, both inputs must be low. 0 and 0 gives you a 1. 0 and 1 gives you a 0. 1 and 0 gives you a 0. 1 and 1 also gives you a 0. Okay. So if set is high, and reset is 0, it doesn't matter what the output is at Q naught. The output of the top gate will always be 1. And then that 1 is fed back to the lower gate. So 1 and 1 gives you a 0. That 0 is fed back to the top gate. 0 and 0, output still remains at 1. So for R is equal to 0 and S is equal to 1, Q output is set to 1 and Q naught is set to 0. Does it make sense logically? NOR gate, once again, the output is high only when both inputs are 0. And that happens, in this case, in this flip-flop, when R is 0 and S is 1. Any questions? Okay, let's look at the other case where R goes to 1 and S goes to 0. If R goes to 1 and S goes to 0, at the lower end, lower flip-flop, we know the output will go high only when Q is 0. So if Q is 0, the output Q naught is 1. That 1 is fed back here to the input of the first flip-flop, or the top flip-flop, and the output Q remains at 0. And that 0 is then fed back to the bottom flip-flop. Q naught stays at 1, which is fed back to the top flip-flop, and Q remains at 0. And the cycle continues. As long as the inputs stay at 1 and 0, the outputs are 0 and 1. Yes. Yes. Yeah. So the question being asked is, does this take place instantaneously? The answer is yes. In the blink of an eye, even faster than that, because just to give you the real life example, CPU clock speeds are now 2 gigahertz and higher. I mean, even 4 gigahertz speed is not uncommon, right? You can buy laptops and desktops with 4 gigahertz speed. So 1 gigahertz, let's say 1 gigahertz is considered slow. 1 gigahertz is 10 raised to 9, right? That's a billion. No, a million. Yeah, billion. Billion clock cycles in 1 second. So faster than we can even think, I would say. I don't know. There's no way to quantify it or, subjectively. It's fast. That's all I can say. It's, so the answer to your question is, yeah, it just happens almost as an instant. Okay. Mm-hmm. Yeah, the output is determined by the input of R and S. I see where your question is going. The output is being fed back into the input. So what happens before it's fed back? Is that what you're saying? Exactly. This happens so fast that, yeah. Yep. And also the last state is where the problem arises. So we have 0 and 1 gives us 1. 1 and 0 gives us 0. Before I get to the last state, let's say we had R as 1 and S as 0. Reset state. Reset means the output has to go to 0, which is what we obtained here. Output is 0. Now, if R goes to 0, what happens? If R goes to 0, nothing happens. The output of this stays at 1. Q naught stays at 1. And 1 is fed back to the top flip-flop. Output of that remains at 0. Hence, the first state, where if the input are both zeros, then the output remains at the previous state, Qn minus 1. Qn minus 1. And that is true for both the second and the third state. And that's why we can also say it has memory. Even though the input is now removed, input has changed, the output remains in the previous state. So it has stored that bit of information. And the last state is where it goes bonkers. It doesn't have any idea what to do. And so it's not allowed because we cannot predict what the output would be. And that is kind of related to your earlier question. If we apply R and S as both 1, obviously systems are designed such that it would never happen. But just say it did happen. If R is 1 and S is 1, we cannot predict what the output is. It depends on which flip-flop was like a split second faster. And so the output could be 1 or could be 0. Unpredictable, hence not allowed. So it's a speed between the two flip-flops on which one gets to the destination first. So whenever it's unpredictable, we say the state is not allowed. We cannot use it. So SR flip-flop is just used as a teaching module, teaching example. Okay. Let's see. The way we would describe this or control this is by something known as a timing diagram. Timing diagram. So now this one doesn't have any clock. This is just the two inputs, R and S. Timing diagram, basically, again, we have time on the x-axis. Voltage current would be on the y-axis, but we simply do not refer to the voltages or currents in these timing diagrams. We simply refer to a high or low state. Okay. So here is S set, and here is R. So between, so this is 2, this is 1, this is 1. So between 1 and 2, S is 1, and R is 0 and 0. If that's the case, and I wish to draw my output, I would take, let me draw this out. Let me see if I can. T, and this would be Q. Q. So 1, 2, 3, 4, 5, 6. Okay. Between 1 and 2, the first 2 clock cycles, set input is 1 and reset is 0. My output is set to 1. So my output is high. Then between 2 and 3, my inputs are 0, 0. What is my output? Previous state. And previous state is 1. And so even for 3, my output remains high. It's 1, 1, 1. Then between 3 and 4, the next clock pulse or the next cycle, set is 0, reset goes to high. That means this output goes to 0. Between 4 and 5, both are 0. Output remains the previous state, which is still 0. This is Qn minus 1. This is also Qn minus 1. And then between 5 and 6, doesn't actually matter. It remains at 0. Between 6 and 7, both are 0. And so output remains in the previous state, and so on and so forth. And that's how we can show the functioning of a system using a diagram known as the timing diagram. Timing diagram allows us to predict or display or show or calculate how a system output would work at any point in time. See, from 7, this is 1, 1, 0, 0, 0, 0, 7, 8, 9, and 10. 0, 0, 0, 0, 0, and 0, and 1. And so from 7 to 8, output goes high. And then for 8, it remains Qn minus 1, so it remains high. Then it's again 1 and 0, so it remains high. 0 and 0, previous state, 0 and 0, previous state. And finally, it reaches 11, and that's when it goes to 0. So previous state, previous state, previous state. All right, questions? Any questions? Everyone clear on what a timing diagram is? Okay. So we talked about clocks, right? Right now, there is no clock to the system, right? So it's not synchronized to anything. Okay. So if there is no clock in the system, we call that as asynchronous. An asynchronous system. So no clock synchronization. The system is known as asynchronous. And if clock input is present, then we call it a synchronous system, synchronized to a clock input. So if you have an SR flip-flop and you wish to synchronize with a clock signal, then we add a couple of AND gates to those two inputs, and we connect one input each of the AND gate and call it the clock. So there is a third input to the flip-flop called RSC. RSC. Truth table for this is given by this table right here. First of all, the 0 and 1 for the clock means is the same kind of square wave pulse, right? Rectangular pulse. So we say it's either 0 or either it's 1. So we can consider it to be like a third input, the third input to the system. If the clock is not present or it's 0, then it doesn't matter what the inputs are. If there is no clock, the output always stays in the previous state. Okay. No clock. Output is previous state. Doesn't matter what you give at the input, the output's not going to change. It's easy to see why. If clock is 0, the output of both AND gates are 0. So if it's 0, 0 going into the flip-flop, output is going to remain in the previous state. Make sense? Right? If you want to synchronize, then the clock must go high. So if the clock goes high, then all other states are in play. But those states remain exactly the same as what we saw in the previous two table for RS flip-flop. 0 and 1 gives us 1, and 1 and 0 gives us 0. 1 and 1 on the RS inputs is still not allowed. It's still unpredictable. Okay, so the clock is not a fix for that unpredictable state. The clock is simply to synchronize the functioning with the rest of the circuit. There are multiple systems in a regular regular controller or microprocessor, right? And so all of those are synchronized using a single clock. So if clock is 0, output remains in the previous state. Clock is 1, that's when the output would function. Everything else about that truth table remains the same. A clocked flip-flop with a preset and clear. Sometimes we want the output to remain at a particular level. Preset means we are setting the output to set. And clear means we are clearing out all the outputs, setting it to 0. So a preset simply means output goes to 1. Clear button means output goes to 0. You're clearing out everything. In that sense, it is kind of like a reset and set inputs to the flip-flop. But a preset and reset, is different from the preset and clear. Preset and clear basically are like push buttons. You press it once, and the output goes either 1. If you press clear, the output goes 0. And so those are implemented by a OR gate, right? If you apply a 2-input OR gate, if you apply 1 to one of the inputs, the output goes high. So if preset is 1, doesn't matter what the other input is, output Q will always remain at 1. If the clear goes to 1, output Q naught goes to 1, Q goes to 0. Make sense? So preset and clear are used when we sometimes have a need to either set the output to 0 or set the output to 1. We are presetting, hence the name preset. Or we clear out any memory, and hence clear. So the truth table for that also remains the same. If you look here, it's a standard truth table for the SR flip-flop. Clock is present. It behaves like a regular SR flip-flop. If there is no clock, or if the clock is 0, then nothing works. If preset is 1, nothing else matters. If preset is 1, output goes to 1. If clear is 1, output goes to 0. And the same thing still remains. This is not allowed. 1 and 1 is not allowed. And preset and clear, obviously, they are both opposites. So you cannot have both inputs high at the same time. System becomes unpredictable. We cannot predict what the output is, right? If you're trying to preset it to 1 and you're also clearing it out at the same time, it's a race against time. Whichever input reaches first is what you would get in the output. It could be 1, it could be 0, no way to predict it, hence unpredictable, hence not allowed. Let's take a pause. Let me know if you have any questions. Any questions at all? Nope. All right. Okay. So one more thing I want to do today is the trigger. Now, we talked about clock signals. Clock signals are on for a certain period of time and off for a certain period of time. So if it's a 1 hertz signal, meaning 1 cycle per second, that means for half a second it's on and half the second is off. 1 gigahertz, meaning 1 billion cycles a second. So it means half the time it's on, the other half the time it's off. Assuming it's a 50% duty cycle, right? 50% means it's on and off in equal times. So sometimes you want to avoid the confusion that might arise because of the clock signal. So instead of the clock signal affecting for the entire time period, meaning if it's like half a second, we don't want it to work for half a second, we make the circuit to be triggered by the edge. And if you've used the oscilloscope, you might have used the function which says negative edge triggered and positive edge triggered, meaning you are beginning your analysis at the rising edge or the falling edge. And I'll explain what it means. Starting from the left, we say signal was 0 here, then it went up, right? Then it went up. So let me draw it up this way. And then it, in terms of time, obviously we are going towards the right. When we go towards the right, time is increasing in positive numbers. Goes down. And so on and so forth. Do the arrows make sense? We are going towards the future as we go on the right of the x-axis. Arrows make sense? So here, where the arrows go up, they are known as a rise. Come down, it's known as a fall. If it rises to a higher value, the value goes from 0 to high, it's rising, hence a rising edge. If it's falling from 1 to 0, then it's a falling edge. We can design systems to function for both a rising edge and a falling edge. If it functions, if a response of a system is initiated because of a rising edge, we call the circuit as a rising edge triggered. If the response of a system is initiated because of a falling edge, we call it a falling edge triggered. Okay, so rising edge trigger and falling edge trigger. Let's see. Any questions? So far, so good. So I'm going to, it's close to 11:45. It's 11:43, 44. I'm going to end class here today. We only have a few slides left, but there is a lot of information that went on in here. There's a lot of new concepts. Okay, so there is no reason for us to rush through things now because we have plenty of time. So review the material, take your time. Let me know if you have any questions. But for now, we'll end class here today. Quiz will be either in person, during class on Wednesday, or if it's not proctored live, if it's offline, then it would be Wednesday and Thursday. Yes. So logic circuits, but not what we covered today from the previous slides. So I'll break it up into multiple pieces, smaller quizzes. We'll get done one on Wednesday or Wednesday, Thursday, and then maybe another one after that. Yeah. All right. Any other questions from anyone? All right. Well, then I'll bid you all a good day, and I will see you all on Wednesday.